Our universe is woven together by a hidden architecture known as the cosmic web. This vast, invisible framework of dark matter and hot gas forms the backbone of everything we see, yet most of its profound secrets remain locked away. By the end of this exploration, you will uncover 25 of the deepest mysteries surrounding the cosmic web's ghostly filaments. We will investigate where half the universe's normal matter has vanished and question if our own galaxy is traveling along one of these colossal threads. What do you believe is the greatest unanswered question about the cosmos? This invisible architecture presents our first great cosmic mystery. How do you map a skeleton you cannot see? The cosmic web's filaments are made predominantly of dark matter, a substance that does not emit, absorb, or reflect light. It is entirely invisible to our telescopes. To perceive this ghostly framework, astronomers must become cosmic detectives, using clever indirect methods to observe its shadow. One of the most powerful techniques is gravitational lensing. The immense mass of a dark matter filament warps the fabric of space-time around it, acting like a lens. When light from a distant galaxy travels through this warped space, its path bends. By studying how the images of these faraway galaxies are stretched and distorted, we can trace the outline of the invisible filament causing the distortion. It is like seeing the silhouette of a hidden object by watching how light bends around it. Another method involves mapping the universe in 3 dimensions through massive galaxy redshift surveys. By meticulously measuring the positions and distances of millions of galaxies, a pattern emerges. The galaxies are not scattered randomly. They align along vast, interconnected lines and walls, tracing out the luminous nodes where the dark matter filaments intersect. We are essentially seeing the streetlights of the universe and using them to infer the layout of the hidden roads connecting them. Yet, this fundamental invisibility remains a profound puzzle. It forces us to acknowledge that most of the cosmic web, the very framework of reality, is built from a substance whose true nature is completely unknown to us. We can see its gravitational effects, but we have no idea what it is. This is not just a minor gap in our knowledge. It is a fundamental challenge to our understanding of the universe's composition and the laws of physics themselves. This shadowy framework leads us directly to the heart of the cosmic web's greatest secret. The filaments themselves are the most compelling evidence we have for the existence of dark matter. Without its gravitational glue, these immense structures could never have formed. In the early universe, the slight ripples in space left over from the Big Bang were amplified by dark matter's relentless pull. Ordinary matter, the stuff that makes up stars and planets, was simply swept along for the ride, funneled into the vast networks we see today. The cosmic web is, in essence, a fossil record of dark matter's invisible hand at work. Yet this success story highlights a staggering gap in our understanding. We can see what dark matter does, but we have absolutely no idea what it is. This is not a minor puzzle. It is one of the most profound unsolved problems in all of physics. Scientists have proposed several candidates for this mysterious substance. One leading idea is a class of particles known as WIMP, or weakly interacting massive particles. As the name suggests, these would be heavy particles that rarely interact with normal matter, passing through our world like ghosts. Another intriguing possibility involves particles called actions, which would be incredibly light and wave-like. For decades, sophisticated experiments deep underground have been searching for the faintest whisper of a WIMP collision. Others are trying to catch an action converting into a photon in a powerful magnetic field. So far, every search has come up empty. We are left with a cosmic architecture built from a material that remains completely unknown to us. How can we hope to understand the universe's grand design when we are ignorant of its most fundamental component? This invisible substance presents another, even more baffling problem. We have not only misplaced the dark matter, but we have also lost half of the normal matter. This is known as the missing baryon problem. Baryons are simply the particles that make up everything you can see and touch, from the stars in the sky to the screen you are watching right now. According to our most precise calculations of the universe's composition, there should be twice as much of this ordinary matter as we have ever been able to find. For decades, astronomers scanned the heavens, adding up all the stars, galaxies, and visible gas clouds, and came up dramatically short. It was as if we had taken a cosmic inventory and discovered half of all the atoms in the universe had simply vanished. Where could they have gone? The leading theory points a finger directly at the cosmic Webs filaments. Scientists believe this missing matter is hiding in the vast, empty stretches between galaxies, woven into the filaments themselves. But it is not in a form we can easily see. This matter is thought to exist as a searingly hot, incredibly thin gas, often called the warm-hot intergalactic medium. Imagine a fog so diffused that a single coffee mug's worth of it would be spread across an area the size of our entire planet. Now heat that fog to 1,000,000 degrees. It does not glow like a star. Instead, it emits a faint, high-energy X-ray signature that is nearly impossible to detect against the background noise of the cosmos. Spotting this ghostly gas is one of astronomy's greatest technical challenges. It requires incredibly sensitive space-based telescopes designed to see the universe in X-ray light. Only recently have we begun to catch tentative glimpses, finding hints of this hot gas in the spaces between massive galaxy clusters. Each new observation is like finding a single, faint thread in an unimaginably large tapestry. The cosmic Webs filaments are not just dark matter highways. They are also the universe's ultimate hiding place, a secret reservoir holding half of all the normal stuff of creation. How do you observe something that is both incredibly hot and almost not there at all? Finding this hidden matter forces us to ask an even deeper question about the cosmic web. What role do these filaments actually play in the birth of galaxies? We often think of galaxies as isolated islands of stars, but the truth is far more interconnected. Galaxies are not born in solitude. They are forged at the crowded crossroads of the cosmic web, where multiple dark matter filaments intersect and merge. These intersections are the universe's greatest construction sites, where the gravitational pull is strongest, funneling vast reservoirs of gas into dense knots. That gas is the raw material for billions of new stars, yet the journey of this gas is a mystery in itself. How does it travel along these cosmic highways from the empty voids into the bustling galactic hubs? We believe it flows in a relatively smooth, steady stream, but the exact process that triggers a galaxy to ignite with star formation from this incoming fuel is not fully understood. It is a delicate balance. If the gas flows too quickly, it might not have time to cool and collapse into stars. If the flow is too slow, the galaxy might starve. Even more puzzling is the role of feedback. When massive stars are born, they live fast and die young, exploding as supernova. These violent explosions blast energy and material back out into the filament, potentially shutting off the very gas supply that created them. It is a cosmic self-regulation system, a cycle of creation and destruction orchestrated along these invisible threads. We are only beginning to understand this intricate dance. How does a galaxy manage its own growth, balancing the constant inflow of gas with these tremendous outbursts that push it away? The filaments are not just passive roads. They are dynamic, living structures that both feed and are shaped by the galaxies they connect. This intricate dance of gas and gravity raises a fundamental question about the galaxies themselves. How do they begin to spin? Look at a spiral galaxy like our own Milky Way, a magnificent pinwheel of stars rotating in a vast, graceful dance. This spin, known as angular momentum, is a fundamental property, but its cosmic origin is deeply puzzling. Where does this immense rotational energy come from? The leading theory points directly to the tug of war within the cosmic web. In the early universe, as a proto-galaxy was forming at the intersection of filaments, it was not simply sitting still. It was being pulled in different directions by the gravitational tides of the surrounding cosmic structure. One filament might have been pulling slightly harder on one side, while another exerted force from a different angle. This imbalance, this cosmic torque, is thought to have set the infant galaxy spinning. It is a concept you can feel for yourself. If you sit in a swivel chair and have someone gently push on one side of your body and then the other, you will start to rotate. The cosmic web performed this same action on a scale of millions of light years. Yet the precise mechanics of this spin transfer remain one of the great unsolved problems. Why do some galaxies become fast-spinning spirals while others are slow, lazy rotators? The answer seems to lie in the specific geometry of the filaments that fed them, the exact angle and timing of those ancient gravitational tugs. Was the galaxy born at a simple crossroads of two filaments, or was it a more complex hub where many threads converged? The history of every galaxy's rotation appears to be written in the architecture of the web that birthed it, but we are still learning how to read this celestial script. We can run sophisticated computer simulations that show the process in action, watching as virtual galaxies are set spinning by invisible threads of dark matter. But matching these models to the vast variety of real galaxies we observe, each with its own unique spin, is an ongoing challenge. The spin of a galaxy is not just a minor detail. It governs how stars form, how solar systems assemble, and perhaps even the potential for life. The cosmic web may have given our own galaxy its initial twirl, setting in motion the chain of events that led to our existence. Our own galaxy is not a stationary island, but a ship sailing through a dark ocean. And for decades, we have known we are moving, pulled by the immense gravitational attraction of colossal structures like the Great Attractor. But the full story of our cosmic journey is stranger than we thought. We are not just being pulled, we are also being pushed. This is the mystery of the Great Repeller. Astronomers mapping our motion through the universe discovered something that defied simple explanation. While we are being drawn toward one dense concentration of mass, we are also being repelled from a vast, seemingly empty region of space, a cosmic void now known as the dipole repeller. The term repeller is a bit of a misnomer. It is not actively pushing us away with some unknown force. Instead, think of it as a cosmic hill we are rolling down. The universe's expansion has stretched this region so thin that its gravitational pull is far weaker than the surrounding areas. It is an underdense void in the cosmic web, a place where the filaments are stretched to their limit and the nodes are few and far between. With so little mass to hold us back, the stronger pull from the crowded areas behind us effectively pushes us away from this emptiness. We are sliding away from the valley and toward the mountain. Yet the true nature of this repeller remains hotly debated. Because it is so empty, it is incredibly difficult to observe directly. How do you map a void? We infer its existence and its shape by studying the motion of thousands of galaxies around it, all of which seem to be streaming away from this same region. It is like deadening the presence of a hole in the ground by watching how water flows around it. The Great Repeller challenges our understanding of the cosmic web's influence. It reveals that it is not just the dense knots of matter that guide the universe's grand choreography, but also the great empty spaces between them. These voids are not passive backgrounds. They are active players, their profound emptiness exerting a gravitational influence that sculpts the flow of galaxies on the largest scales. What other invisible landscapes are silently shaping our path through the cosmos? This discovery of cosmic voids and repellers reveals a universe of profound contrasts, but the filaments themselves hold an even more baffling secret. We have long pictured these intergalactic threads as rivers of searing hot gas, yet astronomers have stumbled upon something that defies all expectation. Woven within these million-degree channels are delicate streams of cold gas and dust. It is like finding ribbons of ice flowing through a river of lava. This is the cold filament conundrum. How can something so fragile survive in such a hostile environment? These cold streams are not just a curiosity. They are a high-efficiency fuel source for galaxies. Hot gas is energetic and chaotic, making it difficult to collapse and form stars. But cold gas is calm and dense, ready to cool further and ignite into stellar nurseries almost immediately upon arrival. Finding these cold streams is like discovering a network of superhighways delivering refrigerated trucks of star-making material directly to a galaxy's core. Their existence, however, presents a monumental theoretical challenge. The space between galaxies is filled with harsh ultraviolet radiation from quasars and nearby stars, which should heat any cold gas back to a superheated state. Furthermore, the turbulent motion within the filament itself, along with shock waves from galactic explosions, should tear these delicate structures apart. For these cold streams to survive their long journey, they must be shielded and stabilized in some way we do not yet fully understand. One possibility is that magnetic fields, woven through the filament like invisible threads, could provide a protective cocoon containing the cold gas and insulating it from the surrounding inferno. Another theory suggests the cold gas might be so dense that it simply cannot be heated quickly enough, like a massive iceberg taking a very long time to melt even in a warm sea. Each new observation of these cold streams forces us to rethink the physics of the cosmic web. They are not just passive conduits, but dynamic, multi-phase systems where the delicate balance between heating and cooling dictates the very growth of galaxies. How do these frigid rivers endure their journey through the cosmic furnace? And what other hidden structures are we missing in the spaces between everything? These frigid rivers flowing through a cosmic furnace hint at a hidden force protecting them. That force may be one of the universe's most pervasive, yet least understood phenomena. Magnetic fields are woven through the very fabric of the cosmic web. We are only just beginning to detect their ghostly presence stretching for millions of light years along the filaments. How do you map a magnetic field across near total emptiness? It is a monumental challenge. Astronomers search for a faint imprint called Faraday rotation. As light from distant quasars travels through a magnetized filament, the magnetic field subtly twists the light's polarization. By measuring this tiny twist, we can infer the strength and direction of the field, like reading a secret message written in the spin of light itself. The discovery of these fields was expected, but their surprising strength was not. They are far more powerful than any simple theory predicted. This is the puzzle of magnetic field amplification. How does a weak, primordial seed field, perhaps generated in the universe's first moments, get boosted to such immense strength across these vast, empty corridors? The leading theory points to the turbulent motions of the searing hot gas within the filaments. As this gas flows, it shears and twists, stretching the magnetic field lines and effectively winding them up tighter and tighter, amplifying their energy. It is a cosmic dynamo operating on an unimaginable scale. These colossal magnetic fields are far from passive. They play a crucial role in the cosmic web's dynamics, acting as a cosmic traffic police for high-energy particles. They guide and confine ultra-high-speed cosmic rays, particles accelerated to nearly the speed of light by supernova and black holes. Without these magnetic highways, these rays would fly off randomly into the voids. The fields channel them along the filaments, focusing their immense energy and potentially influencing the evolution of entire galaxy clusters. Yet their most critical role might be the one we suspected earlier, providing the structural integrity for those mysterious cold streams. The magnetic fields could create a protective sheath around the frigid gas, insulating it from the surrounding heat and preventing it from being torn apart by turbulence. This intricate interplay between magnetism, superheated plasma, and cold gas is a frontier of plasma physics, a puzzle that connects the very largest structures in our universe to the fundamental behavior of matter. How did these invisible threads of force come to be, and what other secrets of cosmic structure do they hold in their silent, powerful grip? These invisible magnetic threads are not static, but part of a living, breathing structure. The cosmic web itself has a life story, one that spans billions of years, and we are only seeing a single frame of the entire movie. Unraveling the web's evolution is a monumental challenge because we cannot watch it change in real time. The light from the most distant galaxies takes so long to reach us that we are essentially looking into the deep past. We have a collection of snapshots, a baby picture, a teenage photo, and a recent portrait, but we are missing the continuous footage of its growth. From these glimpses, we know the web has transformed dramatically. In the universe's youth, filaments were denser, more numerous, and more tightly interconnected. Galaxies were closer together, and gas flowed more readily along these bustling cosmic highways. As the universe has expanded over billions of years, this intricate tapestry has been stretched. Some filaments have thinned to the point of breaking, disconnecting galaxies from the nourishing flow of intergalactic gas. Others have thickened as the relentless pull of gravity draws more matter into the main superhighways. This evolution is a cosmic tug of war between two titanic forces. Gravity works to pull matter together, to build and maintain the web structure. Dark energy, the mysterious force driving the universe's accelerated expansion, works to tear it apart. As dark energy becomes more dominant, it acts against gravity, pushing galaxies further apart and stretching the filaments that bind them. We are living in an era where this struggle is reaching a turning point. The cosmic web is still forming in some places, while in others it is already beginning to fray and dissolve. What did the web look like when the first galaxies were lighting up? And what will it become in the far future when dark energy has stretched the universe into a thin, cold haze? Our snapshots are precious, but they leave us guessing at the true story of this cosmic architecture's birth, life, and ultimate fate. This grand cosmic tug of war between gravity and dark energy leads us directly to one of the most pressing crises in modern cosmology, a puzzle known as the Hubble tension. At its heart is a simple yet devastating disagreement over how fast the universe is expanding right now. We have two primary ways to measure this expansion rate called the Hubble constant. One method looks at the early universe using the afterglow of the Big Bang as a cosmic ruler. The other method observes the local, modern universe, measuring the distances and speeds of nearby stars and galaxies. Both methods are incredibly sophisticated, yet they stubbornly refuse to agree. The local measurements consistently give us a faster expansion rate than the early universe measurements predict. This is not a small statistical fluke. It is a significant discrepancy that suggests a fundamental flaw in our standard model of cosmology, a model that has been incredibly successful for decades. Where is this error hiding? One of the most compelling suspects is the cosmic web itself. Our standard model assumes the universe is smooth and homogeneous on the largest scales, like a perfectly risen loaf of bread. But we know this is an approximation. The cosmic web reveals a universe that is lumpy and structured, filled with dense filaments and vast, empty voids. What if our local measurements are being skewed because we live inside one of these lumps? Imagine you're trying to measure the average density of the Earth, but you are standing at the bottom of the Mariana Trench. Your local measurement would be wildly off because you are in an extreme, unrepresentative location. Some cosmologists propose we are in a similar cosmic situation, a relative void or an overdense region that is subtly distorting our view. The gravitational pull of a nearby filament or the push from a local void could be gently tugging our entire galactic neighborhood, adding an extra velocity to our motion that we mistake for the universe's overall expansion. Alternatively, the complex gravitational landscape of the web could be acting like a series of lenses, bending the light from distant supernova in ways we have not fully accounted for, throwing off our distance measurements. If true, this means the Hubble tension is not a crisis of physics, but a crisis of perspective. It would mean we have not yet learned to correctly read the cosmic map from our particular location within its vast filamentary structure. Solving this tension is not just about getting a number right. It is about truly understanding our place in the cosmic architecture and determining whether we need to redraw the fundamental blueprint of the universe itself. This blueprint of the cosmic web was not drawn at random. Its intricate pattern is a fossil, a direct imprint from the universe's first fleeting moments. The distribution of its vast filaments and empty voids whispers secrets about a period of unimaginable expansion called inflation, which occurred a fraction of a second after the Big Bang. During this inflationary burst, the universe swelled from subatomic size to something macroscopic, and in the process, microscopic quantum fluctuations were stretched to cosmic proportions. These tiny ripples in the fabric of space-time became the gravitational seeds for everything that followed. The denser spots in this primordial ripple pattern over billions of years pulled in more and more dark matter and gas, eventually evolving into the intersections of filaments we see as galaxy clusters today. The emptier regions became the great cosmic voids. The entire cosmic web is in essence a magnified map of those first quantum whispers. But the most elusive whisper of all is the signal from primordial gravitational waves. These are not waves in water or air, but literal ripples in the fabric of space-time itself, generated by the violent throes of the infant universe. Detecting the imprint of these waves within the cosmic web structure would be one of the most profound discoveries in cosmology, a direct line back to the universe's birth. The challenge, however, is immense. Over 13.8 billion years, the simple initial conditions have been scrambled by a complex history of gravitational collapse, galaxy formation, and violent astrophysical events. The pristine primordial signal is now buried under eons of cosmic evolution. It is like trying to hear the first note of a symphony after the entire orchestra has been playing for hours. Astronomers are now developing incredibly sophisticated statistical tools to analyze the large-scale structure of the universe, searching for subtle, telltale distortions in the alignment of galaxies and filaments that could only have been caused by those ancient space-time ripples. Finding this signal would not just confirm our theories of inflation. It would tell us what powered that colossal expansion, revealing physics at energy scales 1 trillion times higher than any particle collider on Earth can ever reach. Can we learn to listen closely enough to hear the universe's very first tremor encoded in the silent architecture that surrounds us? Even the great voids are not truly empty. Stretching across these desolate cosmic deserts are the faintest ghosts of filaments, threads of matter so tenuous they defy our basic understanding of structure itself. These are the void filaments, and their very existence is a profound puzzle. They form in the least likely of places, the immense regions of space where the cosmic web is at its most sparse. Here, the gravitational pull of matter is at its absolute weakest. According to our models, these are the places where the cosmic web should be at its simplest, with only the faintest wisps of structure. Yet, against all odds, we find these delicate bridges spanning millions of light years of near-nothingness. How can such intricate structures assemble where gravity has so little to work with? In the dense nodes of the web, gravity is a powerful, fast-acting sculptor, quickly pulling matter into thick strands and dense clusters. But in the voids, gravity is a whisper. It has had far less time to act as the expansion of the universe works to pull these regions apart even faster. For a void filament to form, matter must somehow coalesce against this cosmic tide, in an environment where the gravitational signals are incredibly faint and travel times between particles are immense. It is like trying to build a sandcastle in a rising tide with grains of sand that are miles apart. One theory suggests these filaments are not built from the inside out, but are instead shaped by external forces. The immense gravitational tides from the surrounding walls and dense clusters of the cosmic web might be stretching and pulling the sparse matter within the void, shearing it into these long, thin ribbons. It is a top-down process where the architecture of the entire cosmic neighborhood imprints itself even on the emptiest spaces. Another possibility is that these filaments are ancient relics, the last remnants of a much denser web from the early universe that has since been stretched and drained of most of its matter. They are the faded scars of a time when gravity was still aggressively building the cosmos. Observing these faint structures is a monumental technical challenge. They contain so few galaxies that mapping them requires surveying colossal volumes of space just to find a single, faint thread. Each discovery forces us to reconsider the subtle, long-range forces that can shape the universe from incredible distances. What do these ghostly bridges tell us about the resilience of cosmic structure, even in the face of overwhelming emptiness? These ghostly bridges in the void endure an environment of profound emptiness, but the great filaments of the cosmic web are bathed in a different kind of extreme. The gas within them is consistently heated to staggering temperatures of millions of degrees. This presents a fundamental thermal mystery. What cosmic furnace is constantly stoked to keep this vast, diffuse gas so blisteringly hot, especially when it exists in the near vacuum of intergalactic space? One of the primary suspects is a process known as gravitational shock heating. As the cosmic web forms and evolves, vast flows of gas are constantly funneling into the filaments from the surrounding voids. When these colossal streams of gas collide and merge, they do not do so gently. They slam into each other at speeds of hundreds of kilometers per second, creating immense shock waves that ripple through the filament. Think of it like a sonic boom, but on a cosmic scale. The tremendous energy of these collisions is converted directly into heat, violently warming the gas to incredible temperatures. It is a continuous process, a side effect of the universe's relentless gravitational construction. Another powerful and more dramatic heating source comes from the hearts of galaxies themselves. When a supermassive black hole at the center of a galaxy actively feeds on surrounding matter, it can transform into a quasar or an active galactic nucleus. This is not a quiet meal. The process releases titanic jets of energy and matter that blast far out into intergalactic space, punching directly into the surrounding filament. These jets act like cosmic blowtorches, dumping enormous amounts of energy into the gas, stirring it up, and superheating it for vast distances. This is a crucial form of feedback where a galaxy regulates its own growth and the growth of its neighbors by violently heating the very fuel supply that feeds it. A third possibility involves a more subtle and pervasive process, turbulent mixing. The gas flowing along a filament is not a smooth, laminar river. It is a chaotic, roiling flow, full of eddies and whirlpools on an unimaginable scale. This turbulence can mix hotter and colder regions of gas, effectively distributing thermal energy throughout the filament and maintaining its high average temperature. Yet, for all these compelling theories, a definitive answer remains frustratingly out of reach. The challenge is disentangling which process is the dominant heater. Is it the constant background roar of gravitational shocks, the sporadic but violent outbursts from black holes, or the steady churn of cosmic turbulence? Or is it a complex combination of all three, their contributions varying from one filament to another? We see the evidence of the heat, a faint X-ray glow that hints at the inferno within. But understanding the exact source of that heat is key to modeling how galaxies evolve, how the cosmic web regulates itself, and ultimately how the entire universe manages its immense energy budget. What is the dominant engine powering this invisible intergalactic oven? These superheated filaments may seem like sterile conduits of raw energy, but they could also be the universe's most unexpected gardens. Could the cosmic web itself play a role in seeding life across the cosmos? This is one of the most provocative and far-reaching mysteries surrounding these vast structures. The idea hinges on a concept known as panspermia, the theory that life or its fundamental building blocks can travel between worlds. While interstellar space is an incredibly hostile environment, the cosmic web's filaments could provide a potential pathway, a series of interconnected channels linking one star system to another. Within these filaments, the dispersal of organic material might not be entirely random. The same gravitational currents that funnel gas into galaxies could also guide solid objects. Picture a vast, invisible river system with asteroids and comets acting as rafts. A planetesimal rich with complex organic molecules, or even hardy microorganisms shielded deep within rock, could be nudged by the gentle, persistent tug of a filament's gravity. Instead of drifting aimlessly for eons, it might be steered on a course that eventually brings it into a new planetary system, where it crashes onto a young, watery world, delivering the ingredients for life. This is not a gentle process, but a violent and chaotic lottery. The odds of a microbe surviving the radiation, the cold, and the final fiery impact are astronomically low. Yet, given the immense timescales and the sheer number of objects moving through the galaxy, it is not entirely impossible. The cosmic web would not create life, but it could dramatically increase its chances of spreading. Think of it as a cosmic mycelial network, a fungal-like web on a galactic scale, potentially connecting biospheres across millions of light years. This remains a highly speculative idea, far from proven science. We have no direct evidence that life has ever traveled between stars, let alone that the cosmic web facilitates the journey. The distances are so vast and the filaments so diffuse that their gravitational influence on a single comet is minuscule. Yet the possibility forces us to confront a profound question. Is life on Earth a singular, isolated accident, or could we be part of a much larger, interconnected biological system, whose threads are woven into the very architecture of the universe? The answer may be written in the silent, invisible currents that flow between the stars. This grand cosmic architecture, so enduring and vast, may not be eternal. The same filaments that built the galaxies are now facing a slow and relentless dissolution. Their ultimate fate is tied to a single, dominant force, dark energy, which is accelerating the expansion of the universe. As space itself stretches faster and faster, the delicate gravitational bonds holding the cosmic web together are being tested. One possible destiny is a gradual and quiet fading. In this scenario, dark energy does not rip the universe apart violently, but simply overwhelms gravity's pull over trillions of years. Galaxies already moving apart would see the filaments connecting them stretch thinner and thinner. The flow of intergalactic gas, the lifeblood of galaxy growth, would slow to a trickle and then cease entirely. Galaxies would become isolated islands, their star formation shutting down as their fuel supply is severed. The cosmic web would not vanish in a cataclysm, but would fade like a ghost, its threads becoming so tenuous they effectively cease to exist. The universe would grow dark, cold, and lonely. But there is a far more dramatic and violent possibility, a scenario known as the Big Rip. If dark energy possesses a specific and potent character, its repulsive force could grow stronger over time. Not only would it push galaxies apart, but it would eventually overcome the forces binding smaller and smaller structures together. First, galaxy clusters would be torn apart. Then, individual galaxies themselves would be shredded, their stars flung into the expanding void. As the acceleration intensifies, planetary systems would be ripped from their stars. Finally, in the last terrifying moments, planets, molecules, and even atoms themselves would be torn asunder by the uncontrollable stretching of space. The cosmic filaments would be among the first large-scale structures to be erased in this apocalyptic unraveling. This is not just the death of the web, but the dissolution of the very fabric of reality. Which of these fates awaits our cosmos? The answer depends entirely on the true, unknown nature of dark energy. Is its strength constant, leading to the slow fade, or is it dynamic, growing until it triggers the ultimate rip? The silent, invisible filaments of the cosmic web are more than just a map of the universe's past. They are a barometer for its future, and their gradual thinning is the first sign of a cosmic end we are only beginning to foresee. These ghostly bridges in the cosmic web seem to hold galaxies in a silent, invisible embrace, but the connection may be far more intimate than we ever suspected. A truly baffling alignment has been observed across the universe. The spins of galaxies are not randomly oriented. They show a distinct preference, a cosmic choreography where a galaxy's axis of rotation often aligns with the very filament it calls home. It is as if each galaxy is a spinning top carefully placed along a string, its rotation parallel to the thread's direction. This discovery strikes at the heart of how we understand angular momentum on the largest scales. Where does a galaxy's spin come from, and why would it choose to align with an invisible road of dark matter? One compelling theory points to the very beginning. In the infant universe, the primordial tidal forces that set the first protogalaxies spinning were directly tied to the geometry of the emerging cosmic web. As matter flowed into those early filaments, the gravitational pull along the filament's length would have naturally induced a spin in that same direction. The galaxy, in essence, inherited its rotation from the architecture that birthed it. Its spin is a living fossil, a memory of its formation billions of years ago. Yet there is a competing and equally fascinating idea. Perhaps this alignment is not a birthright, but something acquired later in life. As galaxies travel along the cosmic web, they can experience a process called gravitational tidal torque. The subtle, continuous pull from the massive filament itself and from neighboring galaxies within that filament could slowly, over eons, nudge a galaxy's spin into alignment. It is a cosmic version of a gentle hand guiding a wobbly top until it spins perfectly straight. This is a battle between nature and nurture on a galactic scale. Was the alignment imprinted at birth, or was it sculpted by the galaxy's environment over time? The answer is crucial because it tells us whether the initial conditions of the universe were so powerful that they dictate the orientation of galaxies today, or if the dynamic, evolving cosmic web continues to shape them. How can we possibly distinguish between these two possibilities? The key may lie in looking deeper into the past. By observing extremely distant and therefore ancient galaxies, we can see if the alignment was just as strong when the universe was young. If it was, the primordial origin gains strength. If the alignment grows stronger with time, the environmental effect takes the lead. Current observations are tantalizing but not yet conclusive, leaving us with a profound puzzle written in the silent spin of countless islands of stars. This silent galactic spin is a memory of ancient cosmic forces, but the web itself holds a more audible echo from the dawn of time. The universe was once a seething hot plasma, a dense soup of particles and light. In that primordial fluid, gravity would try to pull matter together into clumps, while the intense radiation pressure would push it apart. This created a rhythmic push and pull, sending powerful sound waves racing outward through the young cosmos. These were not sound waves as we know them, but spherical pressure waves traveling at over half the speed of light. Then, the universe cooled just enough for atoms to form, allowing light to travel freely in what we call recombination. In that instant, the waves froze in place, their progress suddenly halted. These fossilized vibrations are known as baryon acoustic oscillations, and they left a permanent, repeating signature stamped across the entire sky. That signature is a preferred scale, a specific distance of about 500 million light-years that became woven into the very fabric of the cosmic web. When we map the universe today, we find that galaxies are statistically more likely to be separated by this exact distance. It is as if the cosmos has a fundamental rhythm, a beat that echoes through the vastness of space. This frozen sound provides cosmologists with a cosmic standard ruler. By measuring the apparent size of these oscillations in the sky, both nearby and in the distant past, we can chart the expansion history of the universe with incredible precision. It is one of the most powerful tools we have for measuring dark energy. Yet, for all its utility, the finer details of how these oscillations sculpted the web remain a subject of intense research. The initial waves were simple, but over billions of years, the complex dance of gravity, gas physics, and dark matter has modified their imprint. The pristine signal has been blurred. How did these simple spherical shells evolve into the complex, interconnected network of filaments and nodes we observe today? Refining our understanding of this transition is like trying to reconstruct a symphony from a single, faded sheet of music, a melody that has been playing since the very first note of creation. These cosmic echoes from the dawn of time provide a precise blueprint, yet when we compare this grand design to our most advanced computer simulations, something vital is missing. The virtual universe looks strangely cluttered. Our most sophisticated models of cosmic evolution, which factor in dark matter, dark energy, and the laws of gravity, consistently predict that the filaments of the cosmic web should be far more intricate than they appear. They forecast a universe teeming with small-scale clumps and dense knots of dark matter, miniature halos that should be woven throughout every filament like beads on a string. But when we train our telescopes on the real cosmos, we find the filaments are much smoother, far more streamlined. It is as if we designed a model of a forest predicting countless twigs and branches, only to go outside and find the trees have surprisingly bare and clean trunks. This is the mystery of the missing small-scale structure. Where are all the predicted dark matter clumps? One compelling possibility points a finger directly at the nature of dark matter itself. The standard model assumes it is cold, moving slowly in the early universe, which allows it to easily form these tiny, dense structures. But what if dark matter is not completely cold? What if it is slightly warm, possessing a small amount of intrinsic motion? This warmth, this tiny thermal energy, would prevent it from collapsing into the very smallest clumps, effectively smoothing out the filaments. It is the difference between pouring sand, which forms fine dunes, and pouring a collection of small, smooth marbles, which would create a much coarser landscape. Alternatively, the answer might lie not with the dark matter skeleton, but with the gaseous flesh upon it. The violent astrophysical processes we have already discussed, the supernova explosions and the jets from supermassive black holes, might be far more effective at cleaning house than we realized. These powerful outbursts could be blasting through the filaments, heating and dispersing the gas so thoroughly that it prevents small clumps from ever coalescing and becoming visible. The cosmic web may be constantly scoured by these galactic winds, erasing the fine details before they can ever fully form. Solving this puzzle is crucial because the amount of small-scale structure is a fundamental test for our entire understanding of dark matter. The smoothness of the filaments is a direct challenge, a clear message that something in our most basic assumptions is either incomplete or entirely wrong. Are we missing a key property of the universe's most dominant material, or have we underestimated the sheer destructive power of the galaxies themselves? The answer is written in the clean, uncluttered lines of the cosmic highways, a quiet rebuke to our most complex virtual universes. The very atoms that make up our bodies were forged in the hearts of long-dead stars, but their journey did not end there. A vast and invisible recycling network woven into the cosmic web is responsible for spreading these heavy elements across the universe. This is the mystery of intergalactic metal transfer. When a massive star explodes as a supernova, or when a supermassive black hole erupts in a violent quasar outburst, it does more than just release energy. These cataclysmic events blast winds of enriched material, a cosmic smog of heavy elements like iron, oxygen, and carbon, far out into the surrounding filament. Galactic winds can stream outward for hundreds of thousands of light years, while jets from active galactic nuclei can punch even further, injecting their metallic cargo directly into the intergalactic highways. This process effectively pollutes the pristine gas of the cosmic web, seeding it with the essential ingredients for rocky planets and, ultimately, life. Yet the efficiency of this vast dispersal system is a major unknown. How much of this precious material is actually captured by other galaxies, and how much is lost forever to the deep voids? Some of this metal-rich gas might cool and fall back onto the galaxy that ejected it in a cycle of cosmic rainfall. Other portions could be swept up by a neighboring galaxy as it travels along the filament, a form of interstellar trade. But a great deal of it may simply remain suspended in the filament, too hot and diffused to ever collapse into a new star. We see the evidence of this pollution everywhere. Even the most remote, seemingly pristine gas clouds in intergalactic space contain trace amounts of heavy elements. The entire cosmic web has been subtly contaminated. But the exact quantities, the flow rates, and the ultimate destination of these elements remain a profound puzzle. How effectively does the cosmos recycle its most valuable resources? The answer dictates the chemical potential of future generations of stars and planets, setting the stage for the possibility of life itself on worlds yet to be born. This grand cosmic recycling system operates on a scale almost beyond comprehension, yet it may be governed by laws operating at the very smallest scales imaginable. The filaments of the cosmic web stretch across billions of light years, but their origin might be traced to a reality where space and time are not smooth and continuous, but fragmented into tiny, discrete pieces. This is the profound mystery of quantum gravity, the long-sought theory that would unite Einstein's general relativity, which describes the gravity shaping the cosmos, with quantum mechanics, the rules governing the atomic and subatomic world. These two pillars of modern physics are fundamentally at odds, and the cosmic web could be the one structure large enough to show us where they meet. How could the web's architecture possibly reflect a granular spacetime? The initial seeds of the web, those quantum fluctuations from the universe's first moments, are a direct hint that the largest structures are tied to the smallest events. If spacetime has a fundamental grain, like the pixels on a screen, then the cosmic web might be the magnified projection of that underlying digital fabric. The specific way filaments connect, their angles, and their persistence across time could be a macroscopic signature of how space-time is woven together at the quantum level. One of the most speculative yet compelling ideas suggests that the cosmic web is not unlike a cosmic neural network, or a graph of interconnected nodes, mirroring the way some theories propose spacetime itself is structured. In this view, every filament represents a fundamental connection, a thread in the tapestry of reality, with each intersection a node where the fabric of space is knotted. The vast empty voids, then, are not true nothingness, but regions where the quantum connections are simply more diffuse. We are not yet able to read this code, but the very pattern of the web could be a direct output of the universe's most basic programming. The challenge, of course, is astronomical. The quantum grain of spacetime is thought to be phenomenally small, at a scale called the Planck length, which is a trillion times smaller than a proton. To see its influence on something as vast as a galactic filament seems impossible. Yet, the immense magnification provided by inflation and 13.8 billion years of gravitational growth may have stretched these quantum imprints to a size we can finally observe. The subtle statistical properties of the web, the precise way galaxies cluster along the filaments, might hide within them the faint, frozen signature of a pixelated universe. Finding that signal would be one of the greatest discoveries in the history of science, a direct glimpse into the quantum engine that built the cosmos. It would mean that by mapping the largest structures in existence, we are, in fact, charting the architecture of reality itself, from the very smallest threads to the grandest cosmic designs. These vast cosmic recycling systems leave behind a unique chemical fingerprint, one we can read in the light of the most brilliant objects in the universe. When astronomers point their telescopes at a distant quasar, they are not just seeing a single pure beacon of light. The quasar's light, on its multi-billion-year journey to Earth, passes through the countless filaments of the cosmic web. And within those filaments float immense clouds of neutral hydrogen, the most basic and abundant element. Each cloud acts like a filter, absorbing a very specific fingerprint of light known as the Lyman alpha line. The result is a stunningly complex barcode imprinted on the quasar's spectrum. This is the Lyman alpha forest, a dense thicket of absorption lines where every single dip and trough corresponds to a different hydrogen cloud at a different distance along the line of sight. It is the most direct evidence we have for the gaseous content of the cosmic web, a shadow play revealing the hidden material between the galaxies. This forest is an incredibly powerful probe. By analyzing it, we can measure the density, temperature, and distribution of the web's primordial gas. We can even trace the subtle effects of gravity and the universe's expansion written into the precise positions of these lines. The enigma is not in seeing the forest, but in mapping its individual trees in 3 dimensions. A single quasar spectrum gives us a one-dimensional core sample, a thin straw pushed through the cosmic web. We get incredible detail along that one line, but we cannot tell if one absorption line is from a small, nearby cloud or a massive, distant structure. It is like listening to a complex symphony played by an orchestra hidden behind a curtain. You can hear every note, but you cannot see which instrument is playing it or where the musician is sitting. To transform this one-dimensional core sample into a true 3-dimensional map, we need a forest of quasars. By observing many quasars in the same patch of sky, we can triangulate. If the same pattern of absorption lines appears in the spectra of 2 nearby quasars, we can infer that a single, large filamentary structure is casting its shadow on both. This is a monumental analytical challenge, a problem of cosmic tomography that requires comparing thousands of incredibly complex spectra. The data sets are so immense that only the most powerful supercomputers can begin to untangle them. We are trying to reconstruct the architecture of an invisible city by only studying the shadows it casts on a few distant streetlights. Each new line of sight adds another thread to the map, slowly revealing the true extent and shape of the cosmic web's most elusive component. How do we translate this beautiful, bewildering symphony of shadows into a precise blueprint of the universe's hidden skeleton? This silent galactic spin finds a bizarre echo in the filaments themselves. A startling recent discovery suggests these colossal threads might also be turning. The idea seems to defy common sense. How can a structure millions of light years long with no central pivot possibly rotate? It is like imagining a river spinning around its own length. Yet, by meticulously mapping the motion of thousands of galaxies within these filaments, astronomers have detected a peculiar signal. Galaxies on one side of a filament appear to be moving slightly toward us, while galaxies on the opposite side seem to be moving slightly away. This systematic flow is exactly the signature you would expect if the entire vast structure were slowly spinning around its central axis. The rotation is incredibly slow, taking many billions of years for a single turn, but the mere possibility is revolutionary. This is the filament rotation puzzle, and it strikes at a core principle of physics. Angular momentum, the same property that makes a galaxy spin, is supposed to be conserved. It cannot be created from nothing. For a galaxy, we can trace its spin back to the gravitational torques from the early cosmic web. But for a filament itself to spin, where could such an immense amount of rotational energy possibly come from? These are the largest structures in the universe, and the idea that they are rotating introduces a problem of scale that current models simply cannot explain. One speculative theory points to the influence of the cosmic web's most dramatic features: the titanic gravitational pull from nearby superclusters, or perhaps the even larger scale shearing flows of dark matter. might be able to transfer torque to a filament, setting it into a slow, ponderous spin. It is as if the entire filament is being gently twisted by the gravitational tides of the cosmic neighborhood. Another, even more exotic, idea suggests this rotation could be a primordial imprint, a fossilized spin left over from the universe's very first moments, woven into the fabric of space-time during inflation and then amplified to a cosmic scale. If confirmed, this faint rotation would force a major revision of our theories. It would mean that angular momentum is generated and transferred on scales we never thought possible, influencing the dynamics of the entire cosmic web in ways we are only beginning to glimpse. The universe's largest structures may not be passive scaffolds, but dynamic entities engaged in a slow, silent dance whose music we are only just learning to hear. These silent, spinning filaments create a labyrinth for the universe's most elusive travelers. Cosmic rays are not rays of light at all, but atomic fragments, protons and atomic nuclei, accelerated to almost the speed of light. They carry more energy than any particle collider on Earth can produce, and for over a century, their origin has been one of astronomy's greatest puzzles. The central problem is that they are not neutral observers. Because they are electrically charged particles, their paths are not straight lines. As they cross the universe, they are bent and twisted by the very same powerful magnetic fields that are woven through the cosmic web's filaments. A cosmic ray that appears to come from one direction in our sky might have actually begun its journey in a completely different part of the cosmos, its path scrambled by a series of magnetic deflections across millions of light years. It is as if we are trying to trace a single, frantic mosquito flying through a house of mirrors, with every mirror constantly shifting and turning. These particles arrive at Earth from all directions, a constant, invisible rain of high-energy messengers, yet their stories are garbled beyond recognition. How can you possibly find the source of a signal when the very wires carrying it are tangled into an impossible knot? The most promising candidates for producing these ultra-high-energy cosmic rays are the universe's most violent events. The colossal jets erupting from supermassive black holes in active galaxies can accelerate particles to these phenomenal speeds. The shock waves from merging galaxy clusters or enormous supernova remnants might also serve as natural particle accelerators. But without a straight path back to the source, we cannot be sure. Every time we detect one of these rare, high-energy particles, it is like receiving a letter with the return address mysteriously scratched out by every post office it passed through. One strategy to solve this is to look for a different kind of messenger altogether. Neutrinos are ghostly particles with no electric charge, which means they fly straight through magnetic fields completely unaffected. If we can detect a neutrino from a cosmic event at the same time we detect a specific pattern of cosmic rays, the neutrino would point directly back to the source, finally giving us a fixed point on the map. Another method involves looking at the highest energy cosmic rays possible. At a certain extreme energy level, a proton should interact with the cosmic microwave background radiation, the leftover glow from the Big Bang, losing energy over long distances. This creates a theoretical horizon, a distance limit beyond which we should not see them. If we can identify a cluster of these ultra-high energy events, their sources must lie within that nearby volume of space, narrowing our search within the cosmic web's local neighborhood. Yet the web's magnetic maze remains a formidable barrier. It transforms the universe from a clear, open sky into a vast and winding hall of mirrors, where the brightest cosmic explosions are hidden behind a shimmering, invisible curtain. What colossal events are we missing, their light replaced by this faint, scrambled rain of atomic fragments? These earliest threads of the cosmic web were spun from almost nothing at all. To understand their birth, we must rewind to a time before the first stars, before the first atoms, when the universe was a dark, seething sea of particles and energy. In that primordial darkness, dark matter was already at work. Its relentless gravitational pull began to sculpt the cosmos, acting on the faintest of blueprints. That blueprint was written in the cosmic microwave background, the afterglow of the Big Bang. This ancient light reveals a universe that was almost but not perfectly uniform. There were tiny variations, minute differences in density and temperature from one patch of space to the next. These anisotropies, these cosmic wrinkles, were the seeds of everything to come. The slightly denser regions held a tiny bit more dark matter, and thus a slightly stronger gravitational pull. Over hundreds of millions of years, these regions acted like cosmic magnets, drawing in more and more dark matter from the surrounding areas. The universe began to collapse along these lines of weakness. Think of a vast, invisible sheet of stretchy fabric being pulled from certain points. The material does not just move toward the points, it also flows along the lines connecting them, creating a network of converging streams. These streams were the infant filaments, the very first bones of the cosmic web. Yet the precise timeline of this collapse is one of the great unresolved puzzles. How long did it take for the first wispy tendrils to truly emerge from the smooth background of the universe? Was it a slow, gradual process, or did it happen in a relatively swift, dramatic phase change? The answers are locked deep in the cosmic dark ages, a period before any stars shone to illuminate the proceedings. We cannot see this era directly. Our most powerful telescopes stare back to the time of the first galaxies, but by then, the web was already mature, its filaments firmly established. We are like an archaeologist who discovers an ancient city and must then deduce how the very first foundations were laid, long before any stones were set. Our best clues come from running the universe in reverse, using supercomputer simulations that model the growth of trillions of dark matter particles. These virtual universes show the filaments emerging naturally from the initial conditions we see in the microwave background, but the simulations also reveal a deep uncertainty. The exact timing and the detailed morphology of the first filaments depend critically on the exact nature of dark matter itself. If dark matter is cold and slow-moving, the first filaments would have formed quickly and been very dense. If it was slightly warm with more intrinsic motion, the formation would have been delayed, and the earliest threads would have been thicker and more diffuse. We are left peering into a fog, trying to discern the silhouette of a structure being built from a material whose very properties remain a mystery. The birth of the cosmic web is the story of how our structured universe emerged from initial chaos, a transformation that set the stage for all of cosmic history, yet its first moments remain hidden in the deepest shadows of time. This final mystery brings our cosmic journey home. Are we living inside a filament ourselves? Our Milky Way galaxy is not floating in an empty void. It is part of a vast celestial metropolis known as the Laniakea supercluster, a gravitational collection of over 100,000 galaxies spanning 500 million light-years. When we map this local universe, a stunning pattern emerges. Laniakea is not a shapeless blob. It resembles a colossal, flattened leaf, with great rivers of galaxies flowing along its veins toward a central, gravitational basin known as the Great Attractor. These rivers are the filaments, and our Milky Way appears to be situated along one of these major threads. We are not at a grand central station, a dense node where many filaments meet, but we may very well be on a suburban cosmic street, a galactic thoroughfare connecting larger hubs. The evidence is still being gathered, but the implication is staggering. If confirmed, it means the very structure that feeds distant galaxies with gas is also our own home. We are not just observers of the cosmic web. We are part of its fabric, residents of one of its grand, invisible avenues. Our entire galactic neighborhood, the sun and all the stars we see at night, are sailing along this dark matter highway. This reshapes our cosmic address entirely. We are no longer just in the Milky Way, which is part of the local group within the Virgo cluster, inside the Laniakea supercluster. We are in the filament. This realization forces a profound shift in perspective. The same forces that sculpted the universe on the largest scale are the forces that shaped our own galactic environment. The gentle gravitational tides that may have set our galaxy spinning, the flow of intergalactic gas that still fuels star birth, even the path of our motion through the cosmos, could all be directed by the local filament we call home. Our place in the universe is not a random point in empty space. We are woven into the grandest structure of all, living deep within the threads of the cosmic tapestry itself. From the ghostly presence of dark matter to the baffling case of the missing baryons, these 25 cosmic puzzles weave a story far grander than any single discovery. We have traced the invisible skeleton of the universe, watched it feed galaxies and set them spinning, and felt the push and pull of its great attractors and repellers. We have found frigid rivers flowing through cosmic furnaces, guided by silent magnetic threads, and pondered if these very filaments could spread the seeds of life itself. We have witnessed the web's ancient birth in primordial sound, and now watch its slow dissolution by dark energy, a fate that remains uncertain. This is not a static architecture. It is a dynamic, living record, a chronicle of the universe's entire history written in filaments of dark matter and hot gas. Its grandest mysteries, from the quantum grain of space-time to the silent spin of its largest threads, remind us that the cosmos is a place of endless wonder. Which of these 25 enigmas captures your imagination the most? Share your thoughts below, and if you are hungry for more journeys to the edge of understanding, be sure to subscribe for our next deep dive into space's greatest enigma.